Welcome everyone to another edition of the Finite Element Seminar at Lawrence Livermore National Lab. It's my pleasure today to introduce Professor Łukasz Kaczmarczyk. He got his degrees from the University of Krakow University of Technology in Poland, and has been at the University of Glasgow, where he's calling us from for almost 20 years. He's a professor there, but you probably know him as the creator and the lead developer of MoFEM, which is a very impressive finite element library, structural engineering, and he's going to tell us about his work in this area. It's all very cool and impressive. I'm sure you will enjoy it. Łukasz, thank you so much for calling us all the way from Scotland and for presenting here. The floor is yours.
Thank you for the invitation. Let me share. So I will tell today about mixed finite element formulation for solid mechanics problem. And as Tanzio said, I am from Glasgow University and working in Glasgow Computational Engineering Center, when we focus our attention of the application of the computational mechanics problems to industrial problems. So I will start immediately with the main point, and then I will argue over the talk more about it. So I will talk mostly about the large deformations and the problems associated with large deformations, in particular when you deal with the nearly incompressible materials. So very often when you're using the high order approximation orders, but as well with the low orders, you end up with the negative Jacobian, and you cannot invert the gradient of deformation. And you lose the polyconvexity, and that triggers lots of problems with the robustness. So what about, instead of approximating of the displacement, approximate directly logarithm of the stretch, which is in our case h, so we can express no Hookean material in the form as you can see below, and then no matrix is inverted, and then when you approximate h on the mesh, for example, the L2 space, then all the coefficients associated with the approximation are real numbers, not real positive numbers. So as a result of that, what we guarantee that for any random set of the degrees of freedom, you will have a positive energy. So that gives us some hope for the more robustness. And I will show how it works over the talk, how it works. Another thing, so then we're using exponential map for symmetric matrices, that to get, when you do exponential map, we can get the stretches. And another thing which we're doing exponential map for the rotations. And this is because we want to, we will enforce the conservation of linear angular momentum in the weak sense, as you will see in the short time. And then just to only say that if this is the SO3 group, or mindful for SO3 group, you can arrive it like that you have this unit element in SO3 group, and then you have increment of the rotation in the Lie algebra space by angle delta theta, and then you compose it with the existing rotation, but you can arrive it to the another point in the different way. So, but now we can, when you do iterations in our scheme, we will closely go to some unique rotation which will be at the equilibrium. And then we will perform this averaging, which will give us at the end symmetry. And when you work with that, you will notice that this is the orthonormal. When you do averaging like that, you at the end get the orthonormal matrix, and then you have this term in the rank 2, order 2, which will give us a quadratic convergence. So then again, we're using exponential map on skew symmetric matrix this time, and before on the symmetric matrix. That that when we compose those rotations and then and the exponential for stretches, we get the polar decomposition on material side. Method itself allowed to do a polar decomposition on the spatial with the spatial stretches, and then you can in fact with this technology which we propose over here invent different decompositions. So this is opening lots of possibilities, and then we scratching only a surface with this particular scheme. Okay, I can show you how to do that. This is the we're solving kind of the industrial problem over here, but we cannot show you actual geometry. So this is a mock bushes from, this is the elements of the car which transfer the vibrations between the elements, and then you can see that with those two exponential maps we can make a nearly incompressible rubber materials with the large deformations, large stretches, self-contacts, and so on. And then I will show you how this all together works. So this is one application which we focus on with our industrial partners. And another application is the contact in the multi-body contact, as you will see later on with the fracture for the elements made from graphite, and which here you have an additional element which shrinks over the time. So then this is represented by SDF, which shrinks over the time, that is pushing the system of the elements. And then I would show you how we get those type of analysis. Again, this is a mixed formulation which those two exponential maps involve. But in that case, we have a small strains, in fact. I will not talk a lot about the multi-body contact, how we resolve it. It's far from perfect at this stage. We don't do a binning, so when you want to scale it for large problems, still we will have probably a problem with the scaling. So, but I will show you how we resolve the contact. Okay. So then I will make argument that structure integrity problems involve plasticity, contact, damage, and fracture, but they have one common thing together. They have unilateral constraints, and those unilateral constraints we resolve with kind of the C function, which has this ridge over here, which is the point where we don't have, when we have to choose one of those planes: plastic active process, elastic process, contact, not contact, or crack propagation or not crack propagation. But in every case, we end up with C functions which we have to resolve. Structure integrity problems, in addition, are tricky to resolve because we're dealing with the heterogeneous materials, very often with the large contrast, complex geometry, and with the messy boundary conditions. So devil in our case is with these unilateral constraints, and I will argue that the mixed elements are like perfect for this case. So in addition, you have to remember that we have to keep the information about the from the constitutive equations. When you deal with the solids remember what you have done to them, so they remember. Fluids forgets, so this makes additional dimension, which difficulty that you have to carry the history. So arbitrary Lagrangian or LLNL formulation becoming even more trickier in those cases. And the mixed elements is again the way how you can deal with it. On top of that, I will argue that all the problems in the structural, difficult problems in structure integrity problems require lower regularity solutions, because we have a plastic fronts, we have a cracks, we have a wrinkling, creases, and caps. In each those cases, you need the lower approximation orders. So then you will use the higher approximation orders to to have a certain structure of the matrix, size of the blocks in order to solve the problems faster. But at the end, you need the lower approximation orders because of those problems with the plasticity, geometrical nonlinearities which generate the instabilities. So very quickly, we're doing everything with MOFEM, and then we MOFEM treat as a way how we can retain the knowledge in Glasgow, and how we can apply that knowledge to the Glasgow to the engineering problems. And then we're working for a long time with the EDF. As well, we're working with the Rolls-Royce, Freidenberg, and then we have a kind of spin-out recently, which is called mesh-oriented solutions. And this is a group of people which actively develop code with me, and this is teamwork. So this is we started MOFEM in 2013, and then we have this idea that we keep the core, and then we have modules with the applications. Core is on MIT license, and then by separating applications from the general abstraction in core, we can separate the implementation. So, for example, when you have in academic environment, when you have a PhD students with joining in, you don't want to drop them immediately into the core if you want to have a bug-free system. So then you have to have this way of the inducing people to the higher and higher abstractions. That's why you have those islands when the modules are different from the core, and then this is changing over the time. Okay, but we don't build everything from scratch. So then this is the ecosystem for MOFEM. When we use PETC from Aragon Labs, we use MOAB. This is like to manage the meshes. We're using material behaviors from by mFront sometimes. It's open source code, and then you can see the whole ecosystem that we try to integrate inside of the core. We provide the Docker containers when it's necessary as well. So then we have a mathematical model, MOAB. We're using MOAB to manage topology. We have PETC to manage algebra, and then in MOFEM core, we manage approximation, are the complexities associated with the finite element approximation, integration, assembly, finite elements, and so on, managing the boundary conditions. And user access that through the interface, and then that is utilized in the user modules. Physics is not implemented in core. User push the operators with own operators with the physics which resolve given problem. So in our development, we aim to have the RAM complex, algebraic energetic spaces on the high approximation orders. We can do discontinuous Galerkin. We can do hybridization, and then it's high level of the abstraction. So we don't know actually what we can do, because our abstraction ultimately can handle the many different problems. But for example, here you have a advection problem with the DG case. All the bases are hierarchical, almost all. We can handle scalar, vectorial, and tensorial bases for all those fields, spaces, and then we have as well the Bernstein polynomial base, but which is not hierarchical, in fact. So for hierarchical, we can do p-adaptivity. For Bernstein bases, we can do uniform rise of the approximation orders. Very quickly, so then we focus on the industrial applications. So we want to have code which can very quickly, from the idea, we can very quickly transfer it to the application where the engineers can run it. So we're doing that by the wanting separation of the modules from core. We try to design the code that we have a large code coverage, but different applications. So, and then in order to achieve, we using this, we utilize the Hollywood model. We don't call you call, we call you, you don't call us. So then user programmer push the operators, the pipelines, and the pipelines depending on the solver, whether you're using linear solver, KSP from PETSI, SNES, or time solver in Emacs, for example. It's calls the certain pipelines in the certain scenario. So that's provide with that design pattern. We have a large code repetition, and then we can even push the whole physics as a bunches to the solvers, and then one application test another application. But what you can see over here in the particular, that when we add the fields, we separate the space from approximation base, because we separate the handling of the degrees of freedom in the algebraic sense from the construction of the base and from the assembly. Those three things are separated on the different abstractions, and they can be tested in the different combinations. So then how it works, so the user push the operators into the pipeline. Pipeline is in fact a finite element, and then you can have a several pipeline which integrate on the volume, pipeline which integrate on the boundary, pipeline which integrate on the skeleton, and then pipeline for right-hand side and so on. And the pipeline has own operators. And operators are executed on the sub-entities on the mesh. So operator is executed on the vertices, edges of the element one by one, faces of the element one by one, and interiors one by one. So thanks to that abstraction, one implementation works practically for all shapes. And then very often when you have implementation, it works for 2 or 3 dimensions and 1 dimensions automatically. So once you test the code on dimension 2 dimensions, automatically, very likely it will work straight away in 3 dimensions. Okay, and then this is important part because we are at the university. So we try to make research applications, but that works for us because when we do the research applications, the code is tested, so we have a better coverage, and then we have we understand that we have to have a bigger user base in order to have a safer code, because then it's a more test, more bug detection. So this is the fracture in the bone from CT scan to mapping density to crack propagation. This is photon diffusion. Here is calculating of light phase from the microscopy. We can then detect the morphology of the liver cell. We're working as well with the people on the atomic force microscopy with the indentation, microfluidics, and then we applied to model the bubbles in the eyes. Geotechnical application of fluid structure applications. But the same abstraction handle practically all those problems. We just choose the right space, right fields, push the right operators into the problems, and then we can solve large set of the problems. So, but the main funding for the long time is associated with the advanced gas cooled reactors. This is the special type of the reactors in the UK when the moderator is a graphite. And this graphite, so then graphite is a moderator, but heat is taken by CO2, and then those operators work on the higher temperature. So then the problem is with those reactors that when the graphite is radiated, it's generate the internal stresses. Those internal stresses cause the fracture, and then there is a need to predict how this fracture will develop. So then we were tasked to devise the mathematical model and numerical model for analyzing the crack propagation. So our model is like, just don't go into the details and moving very fast, is that we have elastic body, which is characterized by state variable of the gradient of deformation and the internal strain energy. This piston represents the work done by external forces, and then at some point, the internal piston, this piston represents the crack front, which makes the crack to propagate. As a result of that, energy is transformed into the crack surface, state variable, which is crack surface, and internal energy of the crack surface. So this is our system, which we try to solve. The movement of the internal piston is characterized by this analog, that this is the Griffith, this is the force which try to move the crack front. This is the Griffith force, and this is the material resistance, which is this is the growth of the crack area, and this is the surface energy created as that. So as you can see, this is what I meant by all the problems in structural integrity problems. Those difficult problems are characterized by unilateral constraint, whether it's a contact with the friction, contact, or plasticity can be represented more or less in the same form. Actually, we in our formulation for crack propagation, we are using we calculating crack front equilibrium directly, implicitly on the mesh, and then we have this complementary function when the Griffith energy at the nodes is equal to resistance, material resistance, then the crack is moving until the new equilibrium is established in the implicit form. That is very complex analysis, strongly nonlinear because it's on the evolving topology. But we can, despite of that, we can yield the results which match the physical reality. This is, for example, when we try to calculate whether the chip can be created. This is the crack was already created, and there is internal stresses which make additional crack to propagate at that corner. And this is the picture from actual reactor. But the problems getting more and more difficult, and then we have to solve the problems like seal ring problem. That as well. This is part which has this complex crack geometry with many contact surfaces. And on top of that, because we evolve the topology directly, we have to manage those complexities that the crack front is on one contact surface, not on the another, and those nodes are moving. That leads us to the problem that we cannot scale, and we start to think about the different solutions. So, but that works. So then we start to think about the mixed formulation, and then we start with this generalized Hoover-Shizu functional. Then this is the so this is the logarithm of the stretch. Then when we I make a mistake over here, should be exponent. When you take the exponent from the logarithm of the stretch, you get the stretch, and then you can calculate the strain energy as I showed on the second slide. So this equation shows us is a consistency between the deformation gradient calculated from the spatial positions. And this is the gradient of deformation approximated by those exponential maps. And that is weighted by the Piora-Kirchhoff tensor. This is work of the body forces, and this is the work of the tractions. So when we look at the stationary stationary point of that functional, you get the consistency equation, and then you can treat that consistency equation further by differentiation by parts. So you enforce the continuity in the weak sense. Then you have a physical equations from when you vary over the stretch or the gradient of the logarithm of the stretch. Then you can get the conservation of the angular momentum. This is the variance of the rotation. You can see over here stretch and Piola-Kirchhoff stress, and finally you have a conservation of the linear momentum. So this is the system of the equations which we will deploy on our problem, and then you will see what will happen later on with that. So naturally, so then practically when you treat that equation by differentiation by parts, you get you enforce that in the weak sense. Every field in your approximation can be, every field in this functional can be approximated in L2 Lebesgue space, except Piola-Kirchhoff tensor. So in other words, we want to satisfy the continuity of the fluxes a priori. And so then tractions boundary conditions will become essential boundary conditions. And then we have a continuity fluxes enforced a priori. We enforce the continuity a posteriori once we solve the system, and then displacement boundary conditions becoming a natural boundary conditions in this formulation. And this system, actually, that system was used to solve this Bush's problem and this problem with this seal ring, which you can have seen at the very beginning. Just quick reminder, so then we understand the H-div space as a space of the functions which are integrable and then square integrable, and then divergence of those functions is as well integrable. So then this base is vectorial as a result of that, and then properties of that space is that you enforce the a priori continuity of the fluxes on the element faces, and the classical example of the finite element base for that is Riviat-Thomas space, which is the subspace, of the H-div space. I will come back to that in a few slides later on. So this is the space. So then what we do, we approximate the Piola-Kirchhoff in H-div and variance in H-div. We approximate the stretches, rotations, and so displacement, rotations, and variance of the displacement and rotation in L2. And we approximate on the mesh logarithm of the stretches. So for any set, so then that system give us that if you will choose randomly degrees of freedom on the mesh, always you will get the finite energy, zero or positive energy. So this H-div space is extended for the stability, how is explained in that paper below, by this bubble function. And this bubble function, so the Riviat-Thomas is vectorial space, but the bubble function in H-div space, this is the tensorial function, which you can see one of those functions over here on this tetrahedral. So this is so-called, this bubble is a zero normal bubble. So it means that the divergence of this bubble is zero everywhere in the volume. And on top of that, there is no flux which going outside. So like circulation of the incompressible fluid inside of the tetrahedral in that case. What I want to say, we limit our application only for tetrahedrals because this is what the industry needs. So then making a meshes for hexahedral meshes is very difficult. Delanoë triangulation is one of the most robust algorithms. So then we want to have our method to work with the tetrahedrons. And then, as you know, that is not so easy when you're dealing with the large deformation and nearly incompressible materials. But thanks to that formulation, everything works well. So we use the mixed elements because we have a separation of the nonlinearities. When you will look at the stationary point of this Hooft-Vargisu functional, you can see that the conservation law is separated from physical equations, and geometrical nonlinearities are separated from the physical equations when you can see about the conservation of angular momentum. That gives a potential for large experimentation because you can integrate those terms differently in time. To some of them you can apply the explicit time integration. For some of them you can apply implicit time integration. You can, when you look at the polar decomposition, you can look at some simplistic schemes how to integrate in time. So then this separation of the nonlinearities gives the large potential for making a robust code. So we satisfy conservation of the momentum a priori, and in fact, the conservation of the momentum is the thing what you can be always is true. Yeah, you not necessarily physical equation is true, but the conservation of momentum is always true. So we satisfy that a priori. Of course, those elements trade the floating point operations, but they trade them to temporal memory access and spatial and temporal memory access. So those elements in some way are going into the direction how the hardware develops. We cannot reduce the latency. Physics constrain us. We can increase the number of chips. So the floating operations in future and now, as you can see through the large language models, is cheap. You have to keep the access to the memory local and in time and in space. And those elements exactly provide that. So you can see why those elements were not successful in 90s, because you want to limit the complexity. But now is a time for the mixed formulations. And because we have this weaker or ultra-weak formulation with the lower regularity, it's perfect for managing those unilateral constraints. So plastic front, fracture, plasticity, geometrical instabilities when the cusps are created, consequence of this separation of the nonlinearities, and then we have more fields. We have a sparse dense block structure, which we can exploit, and then it's kind of the method is future hardware ready. This is my argument, and then I will argue for mixed formulations as a result of that. Okay, so just to remind you that we will be working with the updated Lagrangian formulation. In that case, we're using this polar decomposition when we're using the exponential map to calculate the rotation, and we're using exponential map to calculate the stretches. I want to say that in the future, you can look for the different decompositions. This is one of the simplest possible decomposition. But if you look into the literature, you can try the other ones, which can be beneficial. So then, but then you can, in addition, you can introduce some intermediate configuration, and then when you working with the updated Lagrangian formulation, so when you work with the total, you don't need intermediate configuration. But if you will work with the updated Lagrangian, you can introduce intermediate configuration, but then you can exploit the nice feature of the mixed formulation that you can, since you approximate the displacements in L2 space, you can project them on the H1 space, and this projection in H1 space you can treat as an intermediate configuration. And in some cases, you can get the higher accuracy. That is very interesting avenue, but not always will work. For a reason why not always these C1 continuous methods works with the large deformations, because once you project L2 space on H1, you can end up for high polynomial orders, you can end up with the situation that the Jacobian locally will become negative, and then it's caused a series of the problems. So what I argue that very severe deformations is very hard to approximate when you enforce the high C1 or CT. But only way when the cusp is created, for example, you have to lower the regularity of the problem. But sometimes when you will want to solve the dynamic problems and so on, and then you want to have this, because from here to there, you can, for example, assume that you have a smaller rotations, large stretches, or from going from here to there, you can assume that you have large rotations and small stretches. So that provides the many ways for different kinds of the linearizations. For one problem, one linearization work, and for another linearization. Again, this mixed element applied to nonlinear problems opens a spectrum of the different possibilities. So this is like a source for the innovation. Okay, so then how I will show you quickly how it works. So for example, when you have a Cook beam classical problem, and then you do p-refinement, and then you can exploit that to calculate the norm. So we can get the solution with the increasing approximation order. The Cook beam is nasty because this is singularity along that edge. So you can see that we can see the error. We quickly remove the error in the middle, but we cannot reduce it over here. And we apply that method for this Moonley-Riven material, as you can see, with these nasty terms, as you can see over here, which is tricky to calculate for classical finite elements. Here you just run it without the need of the reduced integration, no dirty trick, you don't have to deploy any dirty tricks. This is the same story with the H refinement. You can see over here how this method performs to the other methods in the literature. We can see to the Peter Virger's paper, Antonio Gil, and Javier Bonet. It's like it's not exact science when you compare those results, but this method, you can see how it works. It's pretty good. You can do, of course, large rotations, apply method to the problems like that one, which is kind of the crazy because you're using solid element with the to model shells. There is some differences because this our element has additional stiffness associated with shear. This is because the reference solution is shell theory, but pretty good agreement. This is different kind of the problem. You can see as well how the comparison with the p-refinement look like, and then as well nice convergence. Just to reassure you that we're doing tests that everything works as it should be. So when we start first with this method, you're getting something which is terrible. This is the matrix, how it look like. So you can see this block with the H-div space, and then you have those many fields over here with the L2 space. You can see the bubble and then bubbles separately from the Rivière-Thomas space on this case. And then what we try to eliminate the logarithm, then we eliminate stress bubble, eliminate the rotations, and we can, with the struggle, we can live with the folding that applying the Schur complements in the sequence, we can arrive only with the H-div space. But that is nasty system to solve. It's much smaller, but in principle is a nasty system to solve. You have to have a dedicated solver for H-div space. You cannot deploy the multi-grid. So this is Newman type of the problem, and this is not appropriate for the multi-grid solvers. So then natural thing is that to look about our old idea. One, I don't know who was first, who introduced that, but you can look at the Buffy about the hybridization. And of course, and there is a nice papers from by Tanzio as well in Siam about algebraic hybridization, which in fact, this is I learned most of the stuff from that thing, that you can introduce another field on the skeleton, and then you can break the H-div space. So the H-div space looks like L2 kind of, but we preserve the structure that still we can, inside of our software, we can associate the traces with the faces and parts with the associated with the interior. So we have a kind of the geometric hybridization, not algebraic hybridization, if I can be clear. So then we getting system like that when we introduce this on that so on skeleton, you introduce the Lagrange multiplier, which is in L2 and on the skeleton, and then it has interpretation of the displacements. And then this Lagrange multiplier is to connect together, enforce the continuity which was broken again. On the first instance, it makes no sense, but in fact, this is the solution for all the problems. Because what you can do, you can calculate the Schur complement. And this Schur complement is a matrix with the beautiful structure, because in 2D, you have 4 neighbor blocks, because in triangle, triangle can have 3 neighbors. Okay, so then you have 4 blocks in the row. And then for 3D, you have in 3D you will have 4 or 5 blocks in the row. So then, and then you know in advance that you don't have no more blocks. So then, when you implement your own data structure for keeping that matrix, you can pre-allocate. You can exploit the fact that you know a lot about the structure of that matrix. So. And then on top of that, calculating Schur complement, because you can do it element by element. So you have this spatial and temporal locality. So you can calculate that Schur complement efficiently. And then you can, we're working now on the GPU solver. We are far away from what we want to have now, but it's like perfect scenario for a GPU solver to calculate Schur complement. So matrix is bidiagonal, and then you can calculate exact Schur complement in that case. And then you just plug in that thing to the field split solver in PETSI, and then through that field split solver, you can deploy, for example, to solve the Schur-Complending hyper, or implement your own preconditioner to it. D itself can be as well very nicely calculated block by block, so then you don't even have to assemble that thing. You can do it on the fly. Again, perfect for the GPU acceleration. Okay, so this is the old plot. We should do it again, but so now it's funny story when you have this hybridized solver. It turns you know about that much more than I do probably. So then you don't now you choose not approximation order to increase your accuracy. You choose it that it fits the block size fits your architecture. What GPU have, what CPU have, and then, for example, in that particular test, the sweet spot was what was with the third polynomial order. So, but once you introduce the hybridized field on the skeleton, you can do many things with it. And then, so we work with the with contact. We step into the difficult problem of the instabilities when you approximate in classical finite elements. You approximate the Lagrange multipliers in H1 space. You have this instability which is propagating into the solution. This is for this test. So of course there is a solution for that with the dual space, well-known solution. But when you have this dual approximation basis associated with nodes, and then you resolve the contact at the nodes. But then the question was still was a question how to make efficient scalable solver for it, how and then how to generate those bases when you have a heterogeneous approximation basis, a polynomial approximation basis. So we come out with this solution that we use the H-div space on the boundary, and then we achieve the stability by integrating in the volume. That was working well. But once we did that step and solved that problem with the instabilities and then resolving the contact area completely. But so you can see, so we have we add the H-div space on the boundary, and then we can so then this is H-div space in the volume, and then traction is a trace of this H-div space on the boundary. So then, and this is acts as a Lagrange multiplier in this case. But once we introduce H-div space, so you can see, and then okay, so then we deployed that. Andre and his PhD student deployed that to the analysis of the rough surface. Thanks to that, he can estimate properly contact area for the real rough surface, which matched the experiment. So on the one side, you can see the experiment. On the other side, you can see the simulation. We get the beautiful agreement. But once we working with the H-div space, which is naturally in our mix element, why we don't have to do all those tricks. We have we can add this L2 space, hybridize L2 space on the skeleton on the faces where we expect to have a contact, and then we can use that hybridized displacement on the boundary to enforce the contact boundary conditions. So very quickly, so then I will show you example with the rigid body. We contact with the rigid body, and we rigid body model by SDF, and then we have a Python function when you can put an arbitrary SDF and then have a contact with that. So when you do that, so then this is our deformable body, this is our SDF, this is normal from the SDF, this is normal from the body. In the spatial configuration, those two things are not necessarily the same. They are the same at the point of the contact. So then when you introduce this C function, as I told you before, and one if positive gap or positive traction, there is no contact. So this function works like that. It's becoming 1 when there is no contact. So when there's no contact, this Q becoming delta Dirac, and as a consequence of that, this equation will enforce 0 traction, free boundary without the traction. From another hand, this is another integral is a forcing term. But from another hand, if we want to enforce the contact, this term will make enforce the displacements in the body such that there is no penetration. So, you can see the simplicity of which hybridization introduced. Suddenly, contact is a natural feature of the whole finite element scheme. And then you can see how this works for the classical problem of the Hertz contact. This is the contact with the second approximation order for the H-div space. So then you can have this H-div contact. So then because we have a constant linear stresses, so then we have this solution, which is good approximation for the given approximation order, but H-div space for second order displacement, third order tractions, which give us this beautiful solution, which gives us this stable tractions revolution. And cherry on the top is that this projection on H1 space automatically provides the information about the approximation order on the displacements. So, but then you can but this hybridization and properties of H-div space automatically enable to introduce the cracking as well, fracture. I will go over quickly. So then when we limit our, there is a surjection. So then so there is a surjection of the H-div space on the tractions, which are in the H-1 half space. But when we limit, so then we can have two different stresses can lead to the same tractions. But when we limit ourselves to the Rivat Thomas space, we'll have this bijection over here. And then we can exploit that fact when we, so this is unit, so then there is one-to-one mapping between the tractions on the faces and the stresses inside. So when we exploit that fact, we can calculate, when we solve the problem, we can calculate the phase release energy after we get the solution. And then when we decide that we want to break the phase, we just simply remove rows and the columns from the matrix, and the crack propagates. And then when we can calculate again release energy, find the when the certain criterion is satisfied, we can release it again and again and again. So then crack propagation practically happens on the linear solver level. That gives us kind of the robustness, which is shared with the phase field method, because in phase field method, crack propagate without the changing mesh topology. And this exactly happens over here. Mesh geometry changing, but topology is fixed. So we have a robust solution for a crack propagation. So this is under the testing by our colleagues in the industry, and this is one of the tests which they're running. And then I can see that simple idea of the breaking a phases by removing rows and columns, adjusting phase position to maximize this function works pretty well, and then gives us crack paths which match the reality. That later on supplemented with H adaptivity with the hanging nodes, and scalability could be a really powerful tool. Okay, I think that I reach the end of the time, so thank you for your attention.
All right, thank you for this really interesting and impressive talk, Łukasz. Get some applause, virtual mostly. A lot of things. I'm sure there'll be questions. Please, if you have a question, just unmute and ask it.
Hi, I'm Mike. Thanks for the talk. I had a question. You did introduce a stabilization parameter, I think, quite early in the talk, and I just wanted to know like how sensitive it is to that stabilization parameter. Well, and I have another question then. So how would this translate into like an explicit finite element formulation? When you come up with time steps, is there some niceness that comes out of that?
I think that we have a version of the simply deploying implicit time integration, but let me show you something. So you can easily introduce the inertia terms in that case, and then integrate things in the time. What makes it super interesting in the future? Imagine that you want to integrate over the fast rotations, that you have something which moving very fast and rotate very fast. So you can, since you approximate the angle of rotation, you can enforce that you can integrate that always the rotation, this tensor is orthonormal. So then you can and then on top of that, imagine that if you have a terms, you can time integrate this term of the gradient of the deformation. So what I say, the extension to the explicit schemes comes naturally to that scheme. And then on top of that, what I say, that you can, for example, imagine that you want to physical equation you can integrate implicitly and other terms explicitly, or opposite. You can assume that, okay, you will treat that this equation in the implicit sense, and then you say that you will treat this physical equation you will integrate it in the explicit sense when your strain energy depending on the rates. So it's a large, because you separate the nonlinearities, there is a large scope for the experimentation.
And like when you have this, is there some sort of history dependence that you kind of develop? Because if you load it and then you unload it, whereas, like you said, the connection between the total Lagrangian and the Lagrangian, updated Lagrangian are the same for, the regular displacement formulations. It's not necessarily the case here. You have, integrals that you have to satisfy when you're doing the exponential methods. Loaded and unloaded, is it going to come back to the same exact spot?
It should be, yeah. So this
Without any error?
Yeah, yeah, it should. Okay, if you treat every nonlinearity as it should exactly, you come back to exactly the same state. Yeah, of course.
Okay.
But most of the problems at the end we're running in the total Lagrangian approach. So this updated approach could be interesting when we go to the dynamic problems, explicit problems, because you can separate the nonlinearities in the more ways. But quasi-static problems usually you will like to do in the total Lagrangian approach.
Right, thanks, Mike. Other questions?
I'll go. I'm another Mike.
Oh, go.
So I thought it was intriguing that you introduced these hybridized displacements on the boundaries, and then you can use them for contact. But I didn't quite follow, like obviously when it's traction free, it's kind of like you want it to go back to how it was. But when you when it's in contact, it seems like there's like essentially a non-smooth jump to like a different decision that you make. Is that different decision essentially like directly applying like you can think about, you have the level set field or whatever, right? And you have to like project that hybridized displacement to the boundary of the level set field, right? Is that something like what you're doing, or is that not quite right? Or is it more of a weak enforcement of the Dirichlet boundary condition?
So thinking about that, if you will have, for example, thermal problem, and you want to have a radiation on the boundary for the mixed formulation, you can add this hybridized field for the temperature on the boundary, or when you have elasticity and then you have a springs on the boundary, you can add the displacements on the boundary. But this hybridized field is simply when you will I will show you. Look, if you have only you want to prescribe the displacements, this term you want to disappear, and on that term you want to just say what displacement you want to have. So you will put difference between approximated US and the U which you want to prescribe on the boundary.
So is it fair to think of it like a penalty contact then, in that sense?
No. Look, so then we have this consistency equation which tells about the consistency between the gradient of deformation and the approximation of the displacement in L2. And then because we enforce this consistency in the weak sense, automatically displacement boundary condition is natural boundary condition.
Okay.
And then
that's fine.
And then look, if I will not have so then if I will put U bar over here, the displacement which I want to prescribe, I will enforce that displacement on the deformation. So then by setting that value to the value which I want to have, I will enforce the displacement on the boundary in the weak sense. Not, I don't say penalty, in the weak sense.
I get it.
I guess how you enforce them. So
let me clarify the question though. Like when you transition from essentially no contact into contact, is there a sort of a discontinuity in how these terms are computed, and does that have any implications for the solver?
So it's a problem. It could be a problem for Newton solver, because you're changing for enforcing zero traction to the enforcing the deformation which satisfy the non-penetration with the rigid body. So then when you look, maybe I will show you where we have. So when you need but that in some sense is no difference to what is happening when you have normal contact. So imagine that this mustache over here is a mustache which enforces the zero traction. So then when you want to have zero traction, you have a terms over here. But when you have a prescribed displacement, that term becoming zero, and the term on the diagonal appears. Yeah. So then contact, when you are contact, you have a terms over here. When you have non-contact, these terms, this is zeroed, and these terms appear. So this is the classical approach when the similar thing happens with the classical enforcement of the contact with the Lagrange multipliers. Only difference here is that this is kind of the dual contact, because our Lagrange multipliers have interpretation of the displacements, when in the classical contact formulation, Lagrange multipliers are tractions. Okay, so it's a dual formulation in that sense.
Yeah, it's very interesting.
But then you have this switch between one and another. So then when we go back to the beginning of the analysis, okay, beginning of my talk, when I introduce this C function, okay, or here, in C function, basically this contact is represented by this function, where here you have a gap, and then we have, and then we switching between those two planes. So this is a kind of the active set. In one case, you making you prescribe the displacement. In the one case, you saying the, so this is plane of the prescribed displacement, and this is plane of zero tractions. Yeah.
Right. Thanks, Mike. Any other questions? Okay, maybe I can ask a few. You mentioned it kind of in passing, but let me ask more explicitly. Do you guys support adaptive mesh refinement?
Yes, we do. But that is not implemented with this. This is going to happen over the summer. This is what you can see with the advection. You can see adaptive mesh refinement. So
and
here is we calculate. This is the upwithing DG. So we calculating jumps, and based on that we adapt the meshes.
And you also kind of mentioned non-conforming. Is it conforming or non-conforming on the simplices?
It's not. It can be both.
Oh, it can be both.
Yes.
And
so here you have here you can see with the high order heterogeneous approximation, and this is not conforming. You can see hanging nodes.
So why would you want to do non-conforming for simplices?
You will not, but but first thing we approximate conforming, and then in fact it's pretty crap because it's making those batch elements.
I see. Now, we can do both too. I'm just curious. Okay.
Historically, we implemented conforming, and this is not so cool. But then we have seen that we have to have this non-conforming.
Okay, and then another clarification. You mentioned you like simplices. I don't think anybody argues about the advantages for meshing, but do you not support hexes at all, or do you choose not to run on hexes?
We support hexes, but when we talk with the people with the industry, when you're dealing with the problems like that, or even like this, or even complex than this, meshing of those things with the hexes is a big problem. It takes a lot of time.
That's understood.
So you want to have a approximation which run on tetrahedrons. This is what you need.
Okay, but I mean this particular one is certainly not that difficult to mesh with hexes, and you could run on the hex version of this.
I don't know. We can run the classical case, but all the implementation for mix.
I see.
I don't know if I not tried. It could be something in the code that I assume that it's always the always a tetrahedron. But in my opinion, you don't want to have a hex in that in those types of the problems.
Yeah, I mean, as you know, it's a trade-off because hexes are much better for GPUs. So
yes,
it kind of.
But imagine when you want to have something as simple as possible, because when you deform those elements, imagine what happens with the Jacobian at the different points. And then when you plug in them into the things like that, or even worse, when you have incompressible Neo-Hookean or Moonley-Ribin, you don't want to have you want to have simplicity. This is my feeling, but I agree. That's why we have higher orders. So then, if we need to bump the block size, so we raise the approximation order. Yeah.
What is a typical order that you? What are the typical orders that you use?
So
in
then
practice?
this is 3. 3 for second for the displacement, 3 for the Piola stress. But if I think that when we finish our work with the GPU implementation, we'll like to have more.
Okay, but you don't run like 8th, 10th order.
Yes, we can. Yeah, we are limited by the quadrature which we are using.
Okay.
Because at some point code will throw error. I cannot generate the high quadrature. But inside of the code there is no limit for the approximation.
I was just asking in terms of practical application. What
we have
do you find useful?
We have one limit on the single entity for single field. We cannot have more than 512 degrees of freedom. So
I think Mike has another question. Mike, you want to unmute and ask?
Oh, it's not urgent, but you're a captured expert in the field, so I can ask questions. So it looks like early on you were showing, you guys were doing some pretty impressive stuff where you were explicitly representing the crack surfaces and sort of evolving the front. And I mean, I'm somewhat aware that that's not trivial to do robustly. And so, but more recently, it looks like you guys have sort of been moving more to the sort of like cohesive, like insertion type of thing. It's not, I mean, I understand it's more elegant in the sense that you don't have to like insert and change topology, but it has the limitation, of course, that the surface representation possibilities are limited, right? You're sort of stuck on the surfaces that exist in the mesh, and that can add some bias and lack of convergence and stuff. So what is your sense of the trade-offs and your sort of view of the future for these kind of trade-offs?
So when we start to talk with the EDF a long time ago, so they want to have high accuracy, high fidelity simulation, which proven to be like that. There is the biggest value of this code in the fracture is that number of the tests were run by Jacobs and EDF, which validated that we can predict actual cracks. On top of that, the cracks which we predicted happened in the future when the reactor was inspected. But now those reactors fracture more and more, and the bigger and bigger systems has to be calculated. So there is no way how we can calculate the system which explicitly propagate the crack, because implicitly, like just because the nonlinearities are big, we will never finish on time our analysis. So now we're moving to this, but in both cases we're using energetic criterion. So in both cases we're using Griffith. We propagate the crack in the direction which is driven by maximal release of energy. But in the method which we propose now, we will not have exact representation of the crack front. When we will add this non-conforming adaptivity, we can approximate it pretty well by simply refining refining mesh at the crack front. But then what we get as back, we'll be able to calculate when the cracks cross each other, nucleate, and so on. But it's not cohesive element because still we calculating release of the energy. So we don't have to break the phase. We don't using a strength criterion. So we don't have a limit when the traction is certain value, we break it. We can, the biggest advantage of this H-div approximation that when we have a H-div space, we know what is the flux of the momentum for a given phase. And then we know that for flux of the momentum, we can calculate what this momentum flowing through the phase, what is the work of it on the strains. So when we so then we know this when we will break that phase, we know what energy will be locally released. Okay, so this is not cohesive type. It's still going back to the Griffith release of the energy, and then we're calculating what is the energy, and that is impossible to do with the classical formulation or even DG, because you will have to actually break the phase, see and calculate the energy difference. Here you don't have to do that. Yeah, so you exploiting H-div space directly. So then it's just kind of the several chickens on one fire, thanks to the hybridization and the separation of the nonlinearities you have with this approach.
Yeah, so when this criteria is reached, like you measure essentially the Griffith energy you dissipate on that surface, and then you break that that space, and then
but you don't break. So then you don't break the phase that you duplicate the degrees of freedom.
Right. They're already duplicated.
It's simply removing, zeroing row and column and putting one on the diagonal, and then automatically crack appear.
Yeah, that makes sense. But when you do that, you do that for the full phase at a time. So essentially the crack in some sense propagates by jumps of one element width in a given load step or something.
Yes, this is what we give comparing to the alt method. But we can say that, okay, we give something, we're getting a massive robustness, we will get the scalability. And then when still we don't throw the old code, so our engineers can run the old code and new code and then see what is the difference when it's necessary.
Mm-hmm.
And then on top of that, when we will add the non-conforming mesh refinement, we can control that error associated with the size of the broken phase. Yeah.
Very cool. Thanks.
Okay. I see Brandon has a question too. Brandon, can you unmute and ask?
Sure. Yeah. This is very interesting, Lucas. But Mike and I have worked a long time ago, in a galaxy far away, on DG methods and cohesive zone questions. So I think we could ask you stuff all day. We won't, but but I did want to this last thing that you said. So I do understand now. So you're snipping, like if you're disconnecting elements a whole face at a time. I'll just point out. I mean, I'm sure you know, like you can get into situations where there's more strain energy in the bulk than you can release on the face. You can get into like unstable. I don't know. It's just you're asking a lot of the solver, I guess, is what I'm saying. Unless you do it dynamically, because you might not have a solution, right? You might have to break everything all the way through to get to
that's mm-hmm. So then that problem is more severe, what you're saying, when you implicitly propagate the crack.
Yeah.
So in that case, we have arc length control.
Yeah.
When we, by arc length control, user prescribe the amount of the crack area which should be grown in one load step. And then load is adjusted to satisfy that criterion. Okay.
Yeah, no, that makes sense.
And that is super important.
Sure.
Because when we're dealing with the problems which involve the contact, we cannot hold the force and propagate the crack.
Yeah.
We have to adjust the force that force release a right amount of the Griffith energy per phase, because when we will not do that, we have a wrong resolution of the contact surface.
Yeah.
So in the case, because we resolve, so then before we break the phase, we can calculate, thanks to H-div space, we can calculate how much energy we release, so we can adjust the load such that we release the Griffith amount of the energy per surface area.
Yeah, that's very nice. I mean, I think there can still be problems where, especially with contact, where you can't, even that regularization wouldn't be enough. But you could always do dynamics or something. There's always another way. So,
but yeah, I agree. But this is where we have to do our compromises.
Yep. Yeah. No, I totally understand. There's no silver bullet for fracture. That's why I was just asking for the things that have sort of the sharp edges that have cut me in the past. Can I ask one other question? It's a quick one, but it's just to make sure I understand. Are the fields that you're actually approximating with finite elements, so for the, I mean, obviously the displacement and the stress, but then it's like the infinitesimal rotation and the log strain. So it's basically like the Lie algebra.
Yeah, exactly.
Elements that you represent, and so then you have to exponentiate them to like change the actual full rotation and the whatever the right Cauchy Green, the U tensor. Okay, so all right.
But with the rotations is easy because you have a Rodriguez formula.
Yeah. It's closed.
Closed form. It's closed form, and then but we do that as well. We approximate the logarithm of the stretches.
Yeah.
And in that case, we calculate the eigenvalues. We exponentiate eigenvalues. Yeah. Only problem is with we have a special module in MOFEM for so-called matrix function that it deals with the problem when the two eigenvalues has the same repeats.
Yeah, or all three, which happens when you start your analysis, right?
Yeah, but then you can deal with that using the hospital rule.
Yeah. That's right. Just really quick though, so do you have a sense that's a lot of really nonlinear fields. I mean, do you have a sense of the inf soup conditions like on your spaces to be able to have a stable method? I mean, you showed the problem that benchmark the Cook's membrane, but do you have some sense of like, you know, Zania was asking about the pollen, you know, what degrees you're using. I mean, do you have a sense of what numbers are allowed, what will actually converge?
All is described in this paper for the like linear case.
Yeah, that's all you can
linear
prove,
elastic
right?
case is well known since 80s.
Okay.
So all is proven and shown. Only since 80s, only development was about to get optimality in the sense to have a minimal number, possible number of degrees of freedom, less and less and less, and that was associated with the choosing the I don't remember with the right bubble, and so you can see the proof from 1988, so from Finland, but the best well known is this in this paper.
Yeah. Okay. So I mean, that's what I would do too. So you look at the linear version and you use the same one and cross your fingers.
Exactly.
I say that like, you know, that's what I would do too. But okay.
So non-linearity should change anything. Yeah. Because then anyway you operate on the some tangent space to the manifold and you solve and then you move to the another. Yeah.
Yeah. So then MoFem can that's nice. So you guys can enrich your element spaces with bubbles.
Yes. So then
you have flexibility to pick different kinds of bubbles and stuff, and you can do that.
Of course, yeah.
Yeah. Okay. Thank you.
But then I want to say that I just forget to say because I was worried about time. So this method has one. So then we guarantee polyconvexity when we evaluate that thing, thanks to approximating of the logarithmic stretch. But we have in these formulations, still we have to deal with the geometrical instabilities, which are physical. Yeah,
exactly.
End up with the buckling and so on and so on.
That's right. You don't want to get rid of those, or you get the wrong answer. But you might want to get rid of them in your preconditioner, or something like that, and just leave them in your.
No, but the problem is with the when things blow up. At some point you have non-unique solution, but
I know.
Yeah,
that's reality, right? That's
Yeah,
what these
but
structures.
you can do, but then because we have this symmetric version of this formulation, and then we have block, so we can condense to the rotations only and study the Hessian, what happens with these eigenvalues. And then when we see instability, for example, we can add the relaxation of the time in order to pass this moment of the cusping, wrinkling, and so on. And this is what we try to do as well. But this is like see this mixed element as a toy, which we don't fully explored. It's many things you can do, much more that you can do with the classical formulations.
Yeah, thanks. I see that.
All right, we're at time. I'm sorry to interrupt this, but we will post the recording of Łukasz's talk and the slides, and feel free to follow up with him. Thanks again for coming and presenting. This stimulates a lot of interesting discussion, Łukasz, and we may be following up with additional questions.